From childhood, most of us have experienced the fascination of magnets. You've likely placed them on refrigerator doors, watched them draw metal paper clips closer, and perhaps brought two magnets near each other to sense that invisible push or pull between them. And I would venture a guess that you've never stopped to question why this occurs. What makes magnets function? What is this enigmatic force that can reach across empty space, acting through the air without any visible connection? The majority of people, if they consider it at all, simply accept it as a given. Magnets attract certain metals. That is just how they behave. It's treated as a simple fact of the natural world. However, it is not a natural fact in the way you might assume. Magnetism is not a basic, inherent property of matter in the same category as mass or electric charge. The real reason magnets work is actually one of the most peculiar and counterintuitive outcomes of quantum mechanics. It is a purely quantum phenomenon. Without an understanding of quantum mechanics, it is literally impossible to grasp why magnets behave as they do. I am Leonard Susskind, and for more than 5 decades, I have been instructing students in quantum mechanics. I can tell you with complete confidence that magnetism is profoundly strange, far stranger than you imagine. The explanation for why a simple refrigerator magnet clings to your fridge involves some of the most profound and bizarre elements of quantum theory. So, let's explore this deeply. Let's truly comprehend why magnets operate. And I assure you, by the conclusion of this discussion, you will never view a simple refrigerator magnet in the same light again. We should begin with the fundamentals. What exactly is magnetism? At its most essential level, magnetism originates from electric charges in motion. If you take an electrical wire and pass a current through it, a flow of electrons, that wire generates a magnetic field around it. Arrange moving charges in a circular loop, and you produce a magnetic field directed through the center of that loop. This is classical electromagnetism, uncovered by scientists such as Ørsted and Ampere in the early 19th century. So magnetic fields are produced by moving charges. That seems clear enough. But here's the puzzle. In a permanent magnet, like a piece of iron or a fridge magnet, where are these moving charges? The electrons within the atoms are not flowing in a continuous current like they do in a wire. The atoms themselves are essentially stationary. So what then is generating the magnetic field? The answer lies in a property called electron spin. And this is precisely where the situation becomes quantum mechanical and truly unusual. Every electron possesses a characteristic known as spin. Despite the name, the electron is not actually spinning. Spin is not like a tiny ball rotating around an axis. That is a misleading classical image, and it is entirely incorrect. Spin is an intrinsic quantum property of the electron. It is an inherent angular momentum that the electron carries even when it is completely at rest. And connected to this angular momentum is a magnetic moment, an extremely small magnetic field. You can picture each electron as a minuscule bar magnet, possessing a north pole and a south pole. However, this magnetic field is not generated because the electron is moving through space. It simply exists as a fundamental attribute of what an electron is. Now, here's the first strange aspect of spin. In classical physics, if an object possesses angular momentum, if it is spinning, you can make it spin faster or slower, and you can orient its spin in any direction you choose. The angular momentum can point anywhere. But in the quantum realm, spin is quantized. An electron's spin can only point in one of 2 possible directions, up or down. When you measure it, you obtain one of 2 discrete values, plus 1/2 or minus 1/2 in units of Planck's constant. That is all. No other possibilities exist. This is fundamentally quantum. There is no classical equivalent for this behavior, and it is absolutely central to understanding why magnets work. So, every electron is a tiny magnet, and it can be oriented either upward or downward. Now, consider a collection of electrons, like those within a piece of metal. The important question is, which way do they point? Do all the spins align in the same direction, or do they point randomly? In the majority of materials, the spins are oriented in random directions, approximately half up and half down, in a completely disordered state. Their tiny magnetic fields mutually cancel, resulting in no overall magnetism. The material is non-magnetic, but in a select few materials, iron, cobalt, nickel, and a small number of others, something remarkable takes place. The electron spins all line up. They all point in the identical direction. Billions upon billions of these atomic-scale magnets become aligned, each oriented the same way. When this occurs, their individual magnetic fields combine. You obtain a macroscopic magnetic field. You have a magnet. But why? Why do the spins align in iron, but not in, say, aluminum or copper? What distinguishes iron? This is where the real physics begins, and this is the point where most explanations of magnetism fall short, because they fail to describe the actual mechanism. They merely state that the spins align and leave it at that. The reason the spins align is due to something called the exchange interaction. The exchange interaction is one of the most elegant and subtle consequences of quantum mechanics that I am aware of. Let me explain it carefully, because this lies at the very heart of the matter. In quantum mechanics, identical particles are truly indistinguishable. You cannot tell one electron apart from another. If you have two electrons and you swap their positions, the physics of the system remains unchanged. The system is symmetric under the exchange of particles. But here is the peculiar part. For fermions, particles with half-integer spin like electrons, the wave function must be antisymmetric under exchange. What does that mean? It means that if you swap two electrons, the wave function must change its sign. It flips from positive to negative, or vice versa. This is the Pauli exclusion principle, and it is absolutely fundamental to all of chemistry, all of solid-state physics, and all of materials science. It is why matter is solid, why the periodic table has its structure, and why you do not fall through the floor. And it is why magnets work. Let me illustrate how this operates. Imagine two electrons close together within a piece of iron. Each electron has a spatial wave function describing its position in space, and a spin state indicating whether it is spin up or spin down. The total wave function for the pair is a product of the spatial wave function and the spin wave function. And this total wave function must be anti-symmetric. It must flip sign when the two electrons are exchanged. There are two distinct ways to make the total wave function antisymmetric. You can have a symmetric spatial wave function paired with an antisymmetric spin wave function. Or you can have an antisymmetric spatial wave function paired with a symmetric spin wave function. If the spins are opposite, one up, one down, then the spin wave function is antisymmetric. Consequently, the spatial wave function must be symmetric. This means the electrons can be close together in space. They can occupy the same general region. However, if the spins are the same, both up or both down, then the spin wave function is symmetric. Therefore, the spatial wave function must be antisymmetric. An antisymmetric spatial wave function possesses a node, a point where it goes to zero, between the two electrons. This effectively keeps the electrons apart. They avoid one another. Now here's the crucial point. Electrons repel each other due to the Coulomb force, the electric force between charged particles. If two electrons are close together, they possess a high electrostatic repulsion energy. If they are farther apart, their repulsion energy is lower. So if the spins are opposite, the electrons can be close together, resulting in high Coulomb energy. If the spins are the same, the electrons are kept apart, resulting in lower Coulomb energy. Therefore, the configuration with parallel spins has a lower total energy. The electrons effectively prefer to have parallel spins because this keeps them separated and reduces their electrostatic repulsion. This is the exchange interaction. It is not a new separate force. It is not something added on top of electromagnetism. It is a consequence of the Pauli exclusion principle combined with the ordinary Coulomb force. It is pure quantum mechanics, and it favors parallel spins. It favors alignment in materials like iron, cobalt, and nickel. This effect is sufficiently strong to overcome the natural tendency toward randomness, and thus the spins align. You get ferromagnetism. Let me be clear about something. This is not obvious. This is not something you could deduce from classical physics. The notion that two electrons with parallel spins are kept apart by quantum mechanics and that this lowers their energy is deeply counterintuitive. But it is exactly what the mathematics tells us, and it is exactly what experiments confirm. The exchange interaction is a quantum mechanical effect with no classical counterpart. You cannot understand magnetism without it, and you cannot understand it without understanding the Pauli exclusion principle. Now you might ask, if the exchange interaction favors parallel spins, why isn't everything magnetic? Why is iron magnetic but copper is not? The answer involves the electronic structure of the atoms. In iron, cobalt, and nickel, there are unpaired electrons in what is called the 3D shell, a particular orbital configuration. These unpaired electrons have spins available to align, and the crystal structure of the metal is such that the exchange interaction between atoms is powerful enough to force alignment across the entire material. In copper, the D shell is completely filled. All electrons are paired, one spin up and one spin down in each orbital. There are no unpaired spins available to align. Therefore, copper is not ferromagnetic. It is a delicate balance. You need unpaired spins, the correct crystal structure, and an exchange interaction strong enough to overcome thermal disorder. Only a handful of elements satisfy all these conditions: iron, cobalt, nickel, and a few others. That is all. But the story becomes even more intriguing. Even within a piece of iron, the spins do not all point in the same direction throughout the entire material. Instead, the material organizes itself into magnetic domains. A magnetic domain is a region, typically a fraction of a millimeter across, where all the spins are aligned in one direction, but different domains are magnetized in different directions. In an unmagnetized piece of iron, you might have millions of domains pointing randomly so that the net magnetic field cancels out. This was discovered by the French physicist Pierre Weiss in 1906. Weiss proposed that ferromagnetic materials spontaneously divide into these domains. He explained this using energy minimization. Here is the reasoning. If all the spins in a piece of iron pointed in the same direction, you would have an enormous magnetic field surrounding the material. Magnetic fields contain energy, magnetostatic energy, stored in the field itself. That energy is proportional to the volume of space the field occupies, and it can be huge. However, if the material divides into domains pointing in different directions, the magnetic fields from different domains can cancel each other out inside the material. The field lines form little closed loops that remain largely within the material. The external field becomes much smaller, or even zero, and the magnetostatic energy is greatly reduced. So, the material wants to break up into domains. It is energetically favorable. But creating domains has a cost. Between two domains, there must be a transition region, a domain wall, where the spins gradually rotate from one direction to the other. Within that wall, neighboring spins are not perfectly parallel, so the exchange energy is slightly higher. The wall itself carries an energy cost. The actual domain structure in a piece of iron is determined by minimizing the total energy, balancing the magnetostatic energy, which favors many small domains, against the domain wall energy, which favors fewer, larger domains. The result is a complex and beautiful structure of interlocking domains, constantly shifting and adjusting. You can actually observe these domains under a microscope using special techniques. They resemble irregular patches, like a mosaic, each magnetized in a different direction. When you magnetize a piece of iron, when you turn it into a magnet, what you are doing is forcing these domains to align. You apply an external magnetic field, and the domains that are already aligned with the field grow at the expense of those aligned against it. The domain walls move, sweeping through the material and converting misaligned domains into aligned ones. If you apply a strong enough field, all domains align. The entire piece of iron becomes magnetized in one direction. And when you remove the external field in a hard ferromagnetic material, the domains remain aligned. They become stuck in their new configuration because the domain walls get pinned by defects in the crystal structure, impurities, dislocations, grain boundaries. The domains cannot easily move back to their original random state. That is a permanent magnet, a piece of material where the domains are all aligned and locked in place. In a soft ferromagnetic material, the domain walls move easily. When you remove the external field, the domains revert to a random configuration, resulting in no permanent magnetization. This is the type of material used in transformers and electromagnets, materials that can be magnetized and demagnetized with ease. Now let me tell you about something that still astonishes me after all these years. At room temperature, iron is ferromagnetic. The domains exist. The spins are aligned within each domain. Everything I have described is in effect. But if you heat iron above approximately 770 degrees Celsius, something dramatic occurs. The ferromagnetism vanishes completely. Above this temperature, known as the Curie temperature, iron becomes paramagnetic. The spins no longer align. The exchange interaction is still present, but thermal energy is now strong enough to overcome it. The spins randomize, and the material loses its magnetism. This is a phase transition, similar to water freezing into ice or boiling into steam. Below the Curie temperature, you have one phase, ferromagnetic, with aligned domains. Above it, you have a different phase, paramagnetic, with random spins. This phase transition is driven entirely by the competition between energy, which wants spins aligned via the exchange interaction, and entropy, which wants spins randomized because there are vastly more possible disordered states. Pierre Curie discovered this effect in 1895, and it is named after him. The Curie temperature varies for different materials. For iron, it is 770 degrees. For cobalt, 1,115 degrees. For nickel, 358 degrees. These numbers are determined by the strength of the exchange interaction in each material. If you cool a piece of iron below its Curie temperature, letting it freeze into the ferromagnetic state, something remarkable happens. The spins spontaneously align. You do not need an external magnetic field. The material on its own decides to break the symmetry and choose a magnetization direction. All the domains pick their orientations. The symmetry of the high-temperature phase, where all directions are equivalent, is broken. This is called spontaneous symmetry breaking, and it is one of the most important concepts in modern physics, appearing in superconductivity, particle physics, and cosmology. The ferromagnetic phase transition in iron is one of the simplest and clearest examples of spontaneous symmetry breaking in nature. Now let me address a point that confuses many people. You have probably heard that moving electric charges create magnetic fields, and I stated at the beginning that magnetic fields originate from moving charges. But I also said that in a permanent magnet, the electrons are not moving around. They are sitting in atoms. So what is the explanation? The answer is that electron spin itself creates a magnetic field. Even though the electron is not moving through space in a classical sense, the spin-angular momentum of the electron is quantum mechanically associated with a magnetic moment. It is as if the electron were a tiny current loop, even though it is not. This is one of those areas where the classical picture breaks down completely. You cannot explain it classically. You simply have to accept that in quantum mechanics, an electron with spin possesses a magnetic moment as a fundamental property of its nature. Paul Dirac figured this out in 1928 when he formulated his famous equation for the electron, the Dirac equation. From that equation emerged, naturally and inevitably, the concepts of electron spin and its associated magnetic moment. Dirac predicted the exact strength of the electron's magnetic moment, and experiments have confirmed it with extraordinary precision. So the magnetism of a permanent magnet originates from the intrinsic magnetic moments of electrons, aligned by the exchange interaction, and organized into domains through energy minimization. Every aspect of this, spin, the Pauli exclusion principle, the exchange interaction, domains, is fundamentally quantum mechanical. You cannot explain any of it using classical physics alone. Let me discuss one more point because I believe it truly highlights how strange and quantum mechanical all of this is. Consider the magnetic force between two magnets, the force you feel when bringing two refrigerator magnets near each other. Where does this force come from? Classically, you might say the magnetic field of one magnet exerts a force on the magnetic dipoles of the other magnet. Opposite poles attract, like poles repel. Simple. But quantum mechanically, it is more subtle. The magnetic field does not directly exert a force in a classical sense. What happens is that the magnetic field of one magnet influences the energy levels of the electrons in the other magnet. Electrons with spins aligned with the external field have a lower energy. Electrons with spins anti-aligned have a higher energy. The combined system of the two magnets seeks to minimize its total energy. The configuration that minimizes energy is the one where the magnetic fields reinforce each other in certain regions and cancel in others. The magnets move physically to achieve that configuration. That movement is the force you feel. But this force is a macroscopic manifestation of a microscopic quantum mechanical energy minimization process involving billions of aligned electron spins interacting through their magnetic moments. And none of this can be understood without quantum mechanics. When I first learned about the exchange interaction as a graduate student, I thought it was one of the most beautiful things I had ever encountered in physics. Here was this subtle quantum effect, the Pauli exclusion principle applied to two electrons, producing a macroscopic force, a force you could feel with your hands, a force that humans have known about and utilized for thousands of years, dating back to ancient China and ancient Greece. People have used magnets for navigation, for compasses, for magic tricks, for 2 millennia, and they had no idea why they worked. They could not have known, because the explanation requires quantum mechanics, and quantum mechanics was not discovered until the 1920s. The ancient Greeks thought there was a soul in lodestones that attracted iron. The Chinese believed magnetic forces were a manifestation of Qi, the life force. These were the best explanations available before modern science. Even after electromagnetism was discovered in the 1800s, even after Maxwell wrote down his equations unifying electricity and magnetism, physicists still did not understand ferromagnetism. They knew moving charges created magnetic fields, but they could not explain why a stationary piece of iron possessed a magnetic field. It took quantum mechanics. It took Pauli, Heisenberg, Dirac, Weiss. It required the entire framework of 20th century physics to finally answer the question, why do magnets work? And the answer is, because of the quantum mechanical exchange interaction arising from the Pauli exclusion principle, combined with the intrinsic spin and magnetic moment of the electron, organized into domains by energy minimization, and stabilized by spontaneous symmetry breaking below the Curie temperature. That is certainly a mouthful, but it is the truth, and it is beautiful. Here is what I want you to remember from this. The next time you place a magnet on your refrigerator, remember that you are manipulating billions upon billions of quantum mechanical electron spins, all aligned by the Pauli exclusion principle, organized into magnetic domains held in place by crystal defects, and exerting a force through their intrinsic quantum magnetic moments. You are harnessing quantum mechanics every single time you use a magnet. You simply do not realize it. And that is what I love about physics. The most ordinary, everyday objects, the things we take completely for granted, turn out to have the most extraordinary explanations. A simple refrigerator magnet is a window into the quantum world if you only know how to look. Thank you for listening. Magnets work because of quantum mechanics, and quantum mechanics is strange and beautiful and